Hello students, welcome to Diksha Karnataka YouTube channel. Today I'm going to discuss top 30 questions in moving charges and magnetism. Okay, so this chapter moving charges and magnetism is important chapter for KCET 2024. Okay, if you analyze previous year papers, every year they ask minimum 3 to 4 questions from this chapter. Okay, so if you are able to solve these questions, that is top 30 question, so it will be assured that so you can solve or you will be able to counter the questions in KCET 2024 from these chapters. Okay, yeah, let us start. Question number 1. Charged particle is subjected to a acceleration in a cyclotron as shown. The charged particle undergoes increases in its speed. Okay, so this is the cyclotron, right? Here these two are Ds, right? Ds are connected to AC source, right? Or oscillator, isn't it? And the magnetic field is outward from the plane, right? Magnetic field is outward from the plane. Okay, now the charge is kept at this point, right? At this point. So what happens here, due to the electric field, okay, due to the electric field, here the first half, right? So due to the electric field, here negative sign and positive sign. Due to the electric field, what happens? The charged particle accelerate, right? It will be so it will accelerate and enters into D. Okay, D2. Because of the magnetic field, it takes circular path. There is no electric field inside the Ds. Okay, D is made up of conductor. Okay, so there is no electric field inside the Ds. So because of the magnetic field, it takes circular path, right? It takes circular path and it exists from D2, right? After taking the circular path, it exists from D2. As soon as it enters the gap between these Ds, what happens? It will start to accelerate towards D1, right? The same thing happens in D1 also, right? Again it will accelerate, right? Then take circular path, again it will accelerate, and so on, so on, so on. At this point, the charged particle will exit with high speed. Okay, so between the D's, the charged particle increases its speed, right? So let's check each option. Option 1, only inside D2, wrong. Inside the D's, the charged particle does not accelerate. Okay, so option A is wrong. Option B, inside D1 and D2 and the gaps, wrong. The gaps only, okay, between the D's only it will accelerate. Only outside D1, wrong. Only in the gap between D1 and D2, correct. So the correct option is D. Okay, yeah. Next question, question number 2. The torque acting on a magnetic dipole placed in a uniform magnetic field is 0. Here the torque acting on a magnetic dipole placed in uniform magnetic field is 0, right? Torque tau equal to 0. Tau equal to 0 when the angle between dipole axis and the magnetic field is, okay, we know that torque tau equal to m cross b. M cross b. What is m? Magnetic moment or magnetic dipole moment. Okay, so in scalar, tau equal to mb sin theta, right? Mb sin theta. Here tau equal to 0, right? Isn't it? Tau equal to 0, which is equal to mb sin theta. So if you solve this, you will get theta equal to 0 degree. Okay, theta equal to 0 degree. So the angle between the dipole axis and the magnetic field is 0 degree. 0 degree. Then only we will get the torque acting on the dipole, magnetic dipole, as 0. So the correct option is D. Okay. Next question. Question number 3. A proton and an alpha particle moving with same velocity. Here V alpha equal to V proton, velocity of the alpha particle equal to velocity of the proton, which is equal to V. Okay, enter a uniform magnetic field with their velocity is perpendicular to the magnetic field. Here magnetic field which is into the plane, okay, and this is the direction of the velocity of alpha particle and proton, which is perpendicular to the magnetic field, right? The ratio of radii of their circular path is, okay, we need to find the ratio of the proton ratio of the radii of the proton to the ratio, here ratio of the radii of the proton to the radii of the alpha particle, okay. Radii of the circular part taken by the proton and radii of the circular part taken by the alpha particle. We know that R equal to m into V divided by QB, right? R equal to mv by QB. How we got this formula? By equating the centripetal force and magnetic force, right? When charged particle takes circular path in a uniform magnetic field, what happens? It experiences centripetal force, right? Isn't it? So that centripetal force provided by magnetic force, right? So from that we will get R, that is radius of the circular path of the charged particle is mv divided by qb, okay, mv divided by qb, okay. So now here for proton, radius of the circular path of the proton rp is equal to mp into v divided by qp into b, right? qp into b, okay. Anyway, so here b is same, v is same, right? So from this I can conclude that r is directly proportional to v divided by, r is directly proportional to m divided by q, right? m by q, m by q. Now take the ratio, right? Take the ratio of rp and r alpha. rp divided by r alpha is equal to mp divided by qp whole divided by m alpha by q alpha. M alpha is mass of the alpha particle, mp is mass of the proton, okay. Now rp divided by r alpha is equal to mp divided by qp whole divided by m alpha. M alpha is mass of the alpha particle, that is 4 times mass of the proton. 4 times mass of the proton divided by charge of the alpha particle is 2 times charge of the proton. 2 times charge of the proton. So now mp by qp will get cancelled. 2 2s are 4. So rp divided by r alpha is equal to 1 by 2 or 1:2. So the correct option is C. Okay. Yeah. Question number 4. A moving coil galvanometer is converted into an ammeter of range 0 to 5 milliampere, right? Here it is converted to a range ammeter ranged 0 to 5 milliampere, okay. So I equal to 5 milliampere. The galvanometer resistance is 90 ohm. The value of G is equal to 90 ohm, okay, 90 ohm. And the shunt resistance has a value of 10 ohm. Here S equal to 10 ohm. If there are 50 divisions in the galvanometer turned ammeter on either side of 0, its current sensitivity is, okay. So we know that current sensitivity Is equal to deflection in the galvanometer theta divided by current I, right? Theta divided by current I, isn't it? In this case I equal to, theta divided by Ig, range of the galvanometer, right? Here number of divisions, theta is number of division divided by range of the galvanometer, right? Range of the galvanometer. Here we need to find the value of Ig, right? How to find the value of Ig? Here we know that Ig into G is equal to I minus Ig into S, right? S is shunt resistance, isn't it? Now we need to find the value of Ig, right? Now Ig into G plus S, solve this equation, okay. Ig into G plus S is equal to I into S, right? Now Ig is equal to I into S divided by G plus S, right? Now solve this. Ig is equal to, I is 5 milliampere, 5 into 10 to the power minus 3 into S. S is 10 ohm, right? into 10 divided by G plus S. G plus S is 90 plus 10, that is 100, right? Now here 10 will get cancelled, so this will be 10 to the power minus 4, right? Now the value of Ig is equal to 5 into 10 to the power minus 4 ampere. Okay, here number of divisions is 50, right? 50 divided by 5 into 10 to the power minus 4, right? So 5 tens are 50, right? Take 10 to the power minus 4 to the numerator, then it becomes 10 to the power 5. So Is is equal to 1 into 10 to the power 5 ampere, okay, per division, ampere per division. Hence the correct option is A. Okay, so this has to be 10 to the power 4. Okay, hence the correct option is A. 1 into 10 to the power 5 ampere per division. Yeah, next question. Question number 5. A straight wire of length 50 centimeter carrying a current of 2.5 ampere is suspended in mid-air by a uniform magnetic field of 0.5 Tesla. Okay, as shown in figure. Okay, this is the figure. Okay, so this is the current carrying wire. Length of the wire is 50 centimeter. Okay, so this is the figure. So they forgot to add the figure. Okay, so the wire carrying current 2.5 ampere. Okay, the direction of the current is from west to east. Okay, suspended in mid-air by uniform magnetic field 0.5 Tesla. Okay, the mass of the wire is, so it is suspended, right? That is, the gravitational force acting on this wire is balanced by magnetic force, right? Isn't it? Now, what is the direction of the force acting on this wire? The direction of the force acting on this wire has to be in upward direction, right? Isn't it? Upward direction, that is F equal to I into L into B, right? F equal to I into L into B. So what is the direction of the magnetic field? The direction of the magnetic field is into the plane. Okay, then only the force will be in upward direction. Okay, so this is the direction of the magnetic field, and the direction of the gravitational force is in downward direction, that is mg. Okay, now equate these two forces. I L B equal to m into g. Okay, I L B equal to m into g. So m equal to I L B divided by g. Now substitute the values. M equal to I is 2.5, L is 50 centimeter, that is 50 into 10 to the power minus 2. Okay, into B is 0.5 Tesla, 0.5 Tesla divided by G. G is 10 meter per second square. So this is 5, right? And M is equal to, here this will be 0.5 into 5 is 2.5, right? 2.5 into 2.5 into 2.5, that is 6.25. 6.25 into 10 to the power minus 2. Okay, 10 to the power minus 2 kg, or we can write it as 62.5 into, 62.5 gram. Okay, 62.5 gram. This is the mass of the wire. So here they have given 62.2 gram. No, this has to be 62.5 gram. Okay, so option C is the correct answer. Okay, yeah. Question number 6. A metallic rod of mass per unit length 0.5 kg per meter is lying horizontally on a smooth inclined plane which makes an angle of 30 degree with the horizontal. Okay, so let us draw the diagram. Here this is the inclined plane. Okay, the rod is lying on this inclined plane horizontally. Yeah, angle of inclination is 30 degree. Okay, mass per unit length of the rod m by L is equal to 0.5 kg per meter. Okay, 0.5 kg per meter. A magnetic field of strength 0.25 Tesla is acting on it in the vertical direction. Okay, so this is the direction of the magnetic field, B equal to 0.25 Tesla, right? Acting on it in the vertical direction. When a current I is flowing through it, the rod is not allowed to slide down. The quantity of current required to keep the rod stationary is, okay, so we need to find the value of I, okay, flowing through the rod, so that the rod is in equilibrium. Okay, yeah. So let us draw the free body diagram. Right here, the gravitational force acting on this rod is mg. So if you resolve this, this will be mg sin theta. Okay, and this is mg cos theta. We don't need to write that one. Okay, don't require to write mg cos theta and all. Okay, so this mg sin theta is balanced by magnetic force, right? Magnetic force is F equal to here I into L into B. In which direction magnetic force is acting here? This is the direction of the magnetic field, right? Magnetic field is in this way, right? And the current is acting into the plane. Okay, so this is the rod, right? Isn't it? The current is moving, or here the current is moving into the plane. Okay, so this is the direction of the current. Current is moving into the plane. Okay, use right hand rule here. Current, magnetic field and force, right? Current, magnetic field, right? And this is the direction of the force, that is towards right, I into L into B, right? Now if you resolve this force, this will be I LB cos theta, right? I LB cos theta. Theta is 30 degree. Now mg sin theta is equal to ILB cos theta, right? Mg sin theta is equal to ILB cos theta. What we need to find here? We need to find the value of I. I equal to mg sin theta by LB cos theta. I equal to mg divided by LB tan theta. Okay. Now I equal to m is here. Okay, m by L is given, right? M by L is 0.5. 0.5 into G is 10 divided by B. B is 0.25 into tan 30 degree, that is 1 by root 3. Now solve this, you will get 11.54 ampere. So the correct option is C. Okay, 11.54 ampere. The next question, question number 7. A galvanometer of resistance 50 ohm is connected to battery of 3 volt along with the resistance 2950 ohm in series. Okay, so here the resistance of the galvanometer is G 50 ohm. It is connected to a battery of here V equal to 3 volt along with the resistance 2950 ohm, that is R, in series. A full deflection of 30 divisions is obtained in galvanometer. Okay, so when the current flows in a through a galvanometer, what happens? It will show full deflection, right? 30 divisions, isn't it? In order to reduce this deflection to 20 divisions, the resistance in series should be, okay, we need to reduce the divisions, right, from 30 division to 20 divisions. So how much resistance we need to connect to galvanometer in series? Okay, yeah. So for that, first we need to find what is the current flowing through the galvanometer, right? When it shows 30 divisions, when it shows full deflection of 30 divisions, right? Okay, here we know that Ohm's law V equal to I into R, right? We need to find the value of I. I equal to applied voltage V divided by R equivalent. Okay, now I equal to V is 3 volt, right? Divided by R equivalent is 2950 plus 50, that is 3000. I equal to 1 by 3000 is 1 by 1000, 1 by 1000 is 10 to the power minus 3. Okay, 10 to the power minus 3 is milli, so 1 milliampere. 1 milliampere. So the current flowing through the galvanometer is 1 milliampere. So it shows 30 divisions, right? Isn't it? It shows 30 divisions. So every division represents 1 by 30 milliampere, right? So one division represents 1 by 30 milliampere, right? So there are 20 divisions, right? Isn't it? We need to reduce 30 division to 20 divisions, right? That is, the current flowing through the galvanometer will be here I dash is equal to 20 divided by 30 milliampere, right? Isn't it? 20 divided by 30 milliampere. So 0, 0 will get cancelled. Here I dash is equal to 2 by 3 milliampere. So what does that mean? That is, we need to reduce the current from 1 milliampere to 2 by 3 milliampere. Understood? We need to reduce the current from 1 milliampere to 2 by 3 milliampere. Okay. So for that, how much resistance we need to add in series? Okay. Yeah. Now again apply Ohm's law. Here V equal to I dash into R dash. Okay. R dash. R dash is effective resistance. Okay. R dash is effective resistance. So now here V is 3 volt, right? So 3 volt equal to I dash is 2 by 3 milliampere, okay, into R dash. Now R dash is equal to 9 divided by 2 into 10 to the power 3, okay, ohm. So 9 by 2 is 4.5, right? So R dash is equal to 4500 ohm, okay. R dash is equal to 4500 ohm, okay. So here this is the effective resistance, right? Isn't it? Effective resistance, that is the resistance which we added in series with the galvanometer resistance, right? Resistance of the galvanometer. So R dash, sorry, the new resistance, okay, here X is equal to R dash minus 50, right, which is equal to R dash is 4500, right? 4500 minus 50, this is equal to 4450 ohm, okay. So this much resistance needed to be added to the galvanometer in series, so that the current reduces from 1 milliampere to 2 by 3 milliampere. So the correct option is C. Okay. Yeah. Next question. Question number 8. A circular coil of wire of radius R has N turns and carries current I. The magnetic induction B at a point on the axis of the coil at a distance √3r from its center. Okay. So this is the circular coil, right? The radius of the circular coil is R. Okay. So it has N turns. Okay. N turns. Okay. It has N turns. Yeah. Carries a current I. Carries a current I. The magnetic induction B at a point on the axis. Point on the axis. So this is the axis of the circular coil. Okay. Point on the axis of the coil at a distance √3r from its center. Right. So what is the magnetic field at this point? Here the magnetic field at this point due to circular coil wire is B is equal to N into, N is number of turns, okay, N into mu naught into I into R square. R is the radius of the circular coil, okay, divided by 2 into R square plus X square to the power 3 by 2. X is the distance between the center of the coil and point where we need to find the magnetic field, right? Now B is equal to here mu naught into N into I into R square divided by 2 into R square plus X is √3r whole square. √3r whole square is 3r square. 3r squared to the power 3 by 2. Okay. Now magnetic field B is here mu naught N I R square divided by 2 into, so this is 4r square, root of 4r square is 2r square, 2r square cube, okay, sorry, root of 4r square is 2r, okay, 2r whole cube is 8r cube, right? into 8 r cube. Here r square will get cancelled. B equal to mu naught Ni divided by 16r. So the correct option is A. Okay, mu naught Ni divided by 16r. Yeah, next question. Question number 9. A proton moves with velocity of 5 into 10 to the power 6 j cap meter per second. Okay, with the magnetic field, with the uniform electric field E vector equal to 4 into 10 to the power 6 2 I cap plus 0.2 j cap plus 0.1 k cap volt per meter, and the uniform magnetic field B vector is equal to 0.2 I cap, 0.2 of I cap plus 0.2 j cap plus k cap Tesla. The approximate net force acting on the proton is, okay, so we need to find the net force acting on the approximate value of the net force acting on the proton, right? So the force acting on the proton, F equal to force due to electric field plus force due to magnetic field, right? Now F vector is equal to, take Q as common, okay, E vector plus V cross B vector, V cross B vector. Now substitute the values, you will get the answer. Substitute the values, okay, you will get the answer in vector form. Then take the magnitude of the value, okay, magnitude of this vector. So F vector is equal to Q is here 1.6 into 10 to the power minus 19 into E vector is 4 into 10 to the power 6 into 2 I cap plus 0.2 j cap plus 0.1 k cap plus V cross B, right? V cross B is here 5 into 10 to the power 6 j cap cross 5 into 10 to the power 6 j cap cross B vector. B vector is 0.2 of I cap plus 0.2 j cap plus k cap. Okay, now F vector is equal to, solve this, okay, you will get F vector, the magnitude of the F vector is equal to 20 into 10 to the power minus 13 Newton. Okay, so the correct option is C. Okay, solve this, you will get the approximate value. Yeah. 10. A solenoid of length 50 centimeter having 100 turns carries a current of 2.5 ampere. The magnetic field at one end of the solenoid is, okay, here we know that the magnetic field at the one end of the solenoid, here this is the solenoid, okay, and magnetic field at the one end of the solenoid, here the ends of the solenoid is B equal to mu naught Ni divided by 2, okay. This is the formula for magnetic field at one end of the solenoid, okay, or either end of the solenoid. Yeah, now we need to substitute the values, that's it. So B equal to mu naught is 4 pi into 10 to the power minus 7 into n. N is, here we need to find the value of n. N is number of turns per unit length, right? Number of turns is 100. 100 divided by unit length, that is 50 into 10 to the power minus 2. The length is 50 into 10 to the power minus 2 into I is 2.5 ampere whole divided by 2. Now B is equal to, here 2.5 into 20 is 50, right? So now 4 5s are 20, right? 5 into 2 is 10, right? So this will be 10 only, right? So the answer is 3.14 into 10 to the power minus 4 Tesla. So the correct option is B. Okay. Yeah. Next question. Question number 11. A strong magnetic field is placed on a stationary electron. Then electron is, option A, moves in the direction of the field. Absolutely wrong, right? So when you placed the electron in a magnetic field, uniform magnetic field, the electron stays at its position, okay. So electron does not move, right? When you give some velocity to the electron, so it will start to move, right? So if the velocity of the electron is perpendicular to the magnetic field, then it will take circular path. If the velocity of the electron or motion of the electron is same as the magnetic field, then the velocity of the electron is in the same direction. There will be no effect on the electron, right? Isn't it? So option A is wrong. Option B, moves in opposite direction of the field, wrong. Remains stationary, correct. Option D, starts spinning, wrong. So the correct option is remains stationary. Yeah. Question number 12. Two parallel wires in free space are 10 centimeter apart. Each carries current of 10 ampere in the same direction. The force exerted by one wire on the other. So this is the long wire, okay? That is, they are asking force per unit length, okay? Two parallel wires in free space are 10 centimeter apart. 10 centimeter apart, okay? And each carries a current of 10 ampere. 10 ampere, okay? 10 ampere. In the same direction, the force exerted by one wire on the other. Okay, so here let us find the magnetic field due to the first wire, okay, due to the first wire at this point, okay. So what is the magnetic field? Direction of the magnetic field. Direction of the magnetic field is into the plane, right? Direction of the magnetic field is into the plane due to first wire, okay. Now the current in the second wire is in upward direction, right? Current in the second wire is in upward direction. So the magnetic field is into the plane, right? The current in the wire is in upward direction and the force is towards left, right? The force acting on the second wire due to the first wire is towards left, okay. First let us find the direction, okay, direction of the forces, that is let us find the nature of the force, whether it is attractive or repulsive, then we can easily find the magnitude, right? Okay. So this is the force acting on the second wire due to the first wire. And let us find the magnetic field at this point, okay. So what is the direction of the magnetic field at this point? The direction of the magnetic field is outward from the plane, right? Outward from the plane, isn't it? So the magnetic field is outward from the plane, right? And what is the direction of the current? The direction of the current is in upward direction and the direction of the force is towards right, isn't it? So the force is attractive in nature, that is, when the wire, the parallel wire carries a current in the same direction, the two wires attracts, these two wires attracts, right? Okay, so let us find the attractive force. Now the force due to current carrying wire F equal to ILB, right? Now force due to current carrying wire F equal to, here I is current carrying on second wire due to the first wire, or current carrying first wire, current in first wire due to the second wire. So F equal to I is current in the second wire, okay. L is length of the second wire, okay. B is magnetic field due to the first wire, or we can write I as 10 ampere in the first wire and L is length of the first wire and B is magnetic field due to the second wire. The value of the force is same, okay. Now F equal to I is here current in the second wire, I2 into L, so I will take L here, okay, F by L into B is field due to the first wire, mu naught into I1 divided by 2 pi r, okay, mu naught into I1 divided by 2 pi r. So now here F by L is F dash, okay, F by L is F dash is equal to mu naught into I1 into I2 divided by 2 pi r. Now F dash is equal to mu naught is 4 pi into 10 to the power minus 7 divided by 2 pi into I1 into I2 is 100 divided by r is 0.1 meter, okay. Now this is 2, right? And this will be 10 to the power 3. Okay. Now F equal to 2 into 10 to the power minus 4 Newton per meter. Newton per meter. Okay. So what is the nature of the force? Nature of the force is attractive. Okay. Nature of the force is attractive. So the correct option is A. Understood? Yeah. Next question. Question number 13. A toroid with thick windings of n turns has inner and outer radii R1 and R2 respectively. If it carries certain steady current I, the variation of the magnetic field due to the toroid with radial distance correctly graphed in. Okay. Here magnetic field due to the toroid. Okay. Magnetic field inside the toroid, so that is B is equal to, or magnetic field due to the toroid B is equal to mu naught n into I. Okay, mu naught into capital N into I, not small n into I. Okay, capital N into I divided by 2 pi r, right? So what is r? R is average radius, right? R1 plus R2 divided by 2, right? So now substitute here. B equal to mu naught n capital N into I divided by 2 will get cancelled, pi into R1 plus R2, pi into R1 plus R2. So that is the magnetic field is 0 when R is lesser than R1. Okay, magnetic field is 0 when R is greater than R1, and the magnetic field is B when R lies between R1 and R2, and it is constant. It is constant. So if you draw the graph B versus R, okay, magnetic field is 0 till R equal to R1, right? From R equal to R1 to R equal to R2, the magnetic field is constant. This is the magnetic field R. Magnetic field is constant. Okay, so then it's 0, right? So the correct option is D. Okay, yeah. Next question. Question number 14. A tightly wound long solenoid has a turns per unit length of radius r. Okay, this is the solenoid. Okay, into the plane. Okay, so this is front view. Carries a current I. A particle having charge q and mass m projected from the point on the axis of a axis, from the point on the axis in a direction perpendicular to the axis. Inside the solenoid, the direction here, inside the solenoid, what is the magnetic field? Magnetic field is straight line, right? So that is into the plane. Okay, into the plane or outward from the plane, depends on the direction of the current, right? So here the electron, okay, or the charged particle projected from the point on the axis, from the point on the axis. This is the axis of the solenoid. Okay, it projected from the point on the axis, direction perpendicular to the axis. Maximum speed of the particle for which particle does not strike the solenoid. So when particle projected in a uniform magnetic field inside the solenoid, it's a magnetic field is uniform, right? Isn't it? When particle projected with velocity v in uniform electric field, what happens? It takes circular path. We need to find the maximum velocity of the electron. Okay, maximum velocity of the electron or speed of the particle, not electron. Okay, sorry, not electron. Charged particle, the maximum speed of the charged particle for which particle does not strike, the solenoid, right? So what is the radius of the circular path? The radius of the circular path is r by 2. It does not strike the solenoid, right? So what we need to find here, we need to find speed, maximum speed, right? Isn't it? So here it takes circular path. So centripetal force provided by magnetic force, right? Now centripetal force is here m v square divided by r, which is equal to FB. FB is q into v into b, right? Q into v into b. B is magnetic field due to the solenoid. Now v will get cancelled. So v equal to q into b into r by 2 divided by m. Now b is mu naught into n into I, right? V equal to here mu naught into n into I into q into r by 2, q into r by 2. So q into r divided by 2 m. So the correct option is B. Okay. Next question, question number 15. Which of the field pattern given below is valid for electric field as well as for magnetic field? Okay. So definitely the first one, second one is wrong. So this is for the first one is for positive charge and the second one is for negative charge, and this is electric field, right? You can say anyway the first two are wrong, right? So now look at option C. Correct, right? The magnetic field is in loop, right? This one is also correct. So whether it indicates the this field line indicates the electric field, yes, right? If the electric field is induced electric field, here the induced electric field is in loop, right? Induced electric field is in loop, right? Isn't it? It's in loop, isn't it? So here the option C, that is this field line or this pattern, represent or valid for electric field as well as magnetic field. Anyway, option D is wrong, right? Look at these two poles. Here it is moving away, right? The field line is moving away. Again here it is moving away. Definitely it is wrong, right? The one side has to be moving away and one side has to be moving towards, right? So option D is wrong. Option C is this field line is valid for electric field as well as magnetic field. So option C is the correct answer. Okay. Question number 16. The magnetic field at the origin due to current element dl vector placed at a point with vector position r vector. Okay. So this is dl vector. Okay. This is dl vector. This is the point P where we are finding the magnetic field. Angle between dl vector and the position vector is theta. So magnetic field at point P due to current element dl vector, I is current flowing through this wire. So dB vector, that is magnetic field at point P due to current element, dB vector equal to mu naught into I into dl vector cross r vector divided by 4 pi r cube. Okay. So what is this? This is biot-savart's law, right? Isn't it? So the correct option is C. Okay. Next question, question number 17. In the given figure, the magnetic field at O. So this is the given figure. Okay, we need to find magnetic field at O, right? So there are three sections, right, or three wires. The first wire, second wire, and the third wire, right? Now, what is the magnetic field at O due to the first wire? Let's say B1 is the magnetic field due to the first wire at O. It is 0, right? And magnetic field due to the second wire. So this is semi-infinite wire, right? We need to find magnetic field at O, right? The one side is at infinity, okay? And the other side is exactly, this point is exactly parallel with the point O, right? Or opposite to the point O, right? That is semi-infinite wire. So what is the magnetic field due to the semi-infinite wire? Magnetic field due to the semi-infinite wire is mu naught I divided by 4 pi r. Then B3, that is magnetic field due to this arc, right? So that is mu naught I divided by 2r into theta. So what is the value of this angle? This angle is 270 degree, right? Isn't it? 270 degree, that is 3 pi by 2, right? Sorry, 2 pi by 3, right? Is it 2 pi by 3? No. 2 pi by 3 is 120, right? So 3 pi by 2. 3 pi by 2 is 270. Yeah. 3 pi by 2 divided by 3 pi by 2 divided by 2 pi. Theta divided by 2 pi, right? So 3 pi by 2 divided by 2 pi. Okay. Now net magnetic field at O is equal to B1, that is 0, plus mu naught I divided by 4 pi r. What is the direction of the magnetic field due to the straight wire or semi-infinite wire? It is into the plane, right? So mu naught I divided by 4 pi r into the plane, right? plus what is the magnetic field due to the semicircular wire at, sorry, what is the magnetic field due to this circular wire, not exactly circular wire, okay, this wire or wire 3 due to magnetic field at O due to this wire, okay, or wire 3 at O. So that will be into the plane again. Direction of the magnetic field is into the plane. So pi will get cancelled. So this will be 3 by 4. So again 8, right? 4 into 2 is 8. So 3 mu naught I divided by 8 R. Right? Now solve this. Now B at O is equal to here 3 mu naught I divided by 8 R plus mu naught I by 4 pi R. Right? Again, this is also into the plane. So the correct option is A. Okay. Yeah, next question. Question number 18. A long cylindrical wire of radius R carries a uniform current I flowing through it. The variation of the magnetic field with distance from the wire is, okay, so this is the wire, right? So we need to find the variation of the magnetic field. This is the wire carrying current I, So we need to find variation of the magnetic field with the distance, right? So what is the magnetic field inside the wire? The magnetic field inside the wire is mu naught I R square divided by 2 pi R cube, right? Mu naught, sorry, here this will be, here the magnetic field inside the wire, right? The magnetic field inside the wire is mu naught I R divided by 2 pi R square, okay? Mu naught I divided by 2 pi R square. This is the magnetic field inside the wire. So B is directly proportional to R, that is value of the magnetic field increases, okay? The value of the magnetic field increases inside the wire as you move away from the axis of this wire, right? Okay, so this is the case, R is lesser than capital R, okay? R is the radius R here. Then what is the magnetic field on the surface of this wire? B equal to mu naught I divided by 2 pi R, right? So the magnetic field is constant on the surface of the wire, right? R equal to R. What is the magnetic field outside from the wire? R is greater than R. This is equal to mu naught I divided by 2 pi R. That is magnetic field decreases inversely, right? So if you draw the graph, B is directly proportional to 1 by R or inversely proportional to R. If you draw the graph, magnetic field increases till small r equal to capital R, then it decreases like this, right? Here B is inversely proportional to R. Here R equal to R. Here B is directly proportional to small r, right? So this is the graph, okay? This is the graph. So the correct option is A, okay? Like this. Yeah. This is the straight line. Okay. Yeah. Next question. Question number 19. A cyclotron is used to accelerate protons, deuterons, and alpha particle, that is helium atom, while existing under similar conditions. The minimum kinetic energy gained by. Okay. So here, so all these atoms or the nuclei existing under the same condition, right? That is, the magnetic field is same, the radius of the circular path is same, okay, and here velocity is also, sorry, velocity is not same, right? Velocity is not same. Now what is the kinetic energy gained by the each particle? In cyclotron, the kinetic energy is equal to half mv square, right? Now kinetic energy is equal to half into m into what is v? V equal to qbr divided by m, right? Now q square b square r square divided by m square, right? M will get cancelled. Kinetic energy is equal to q square b square r square divided by 2m. Okay, from this I can conclude that kinetic energy is directly proportional to q square divided by m. Okay, so now compare here. The kinetic energy of the proton is equal to, here constant is b square r square, okay, constant into q square, that is qp square divided by mp. For deuteron, kinetic energy for deuteron is equal to c into, what is the charge of the deuteron? Charge of the deuteron is 2 times charge of the deuteron is same, right? Charge as the charge of the proton, that is qp square divided by, what is the mass of the deuteron? Mass of the deuteron is 2 times mass of the proton, right? And then kinetic energy of the alpha particle is equal to c into q alpha. Q alpha is 2 times qp, right? So 2 times qp squared, right? 2 times qp squared, that is 4 qp, right? Isn't it? Divided by m. M is mass of the alpha particle, that is 4 times mass of the proton, right? So kinetic energy of the alpha particle is equal to c into qp square divided by mp, same as the kinetic energy of the proton, right? So the here kinetic energy of the deuteron is 1/2 times kinetic energy of the proton, that is the minimum kinetic energy gained by the deuterons. Okay, so the correct option is A. Next question, question number 20. Two long straight parallel wires are distanced 2d apart. Okay, they carry steady equals currents flowing out of the plane. Okay, they carry equal steady current flowing out of the plane. Okay, out of plane of the paper. The variation of magnetic field B along the line xx dash given by. Okay, so here we need to find the variation of the magnetic field along the line xx dash, right? Let us find the point where the net magnetic field is 0. Okay, so net magnetic field is 0, that is magnetic field due to this wire is equal to magnetic field due to the other wire. Magnetic field due to the first wire is equal to magnetic field due to the second wire. Okay, so let's say here these two are wires, right? At this point the magnetic field is 0. Okay, magnetic field is 0, the remaining will be d minus x, right? The net magnetic field is 0. Okay, the remaining is d minus x, right? Now magnetic field due to the first wire, okay, magnetic field due to the first wire is mu naught I divided by 2 pi x, which is equal to magnetic field due to the second wire, mu naught I divided by 2 pi into d minus x. Okay, mu naught I by 2 pi, will get cancelled. So if you solve this, you will get x equal to d. Okay, x equal to d. The magnetic field is 0, right? At x equal to d, magnetic field is 0. I will draw here. I will draw the variation of magnetic field along the line xx dash. So at this point, magnetic field is 0, right? This is the first wire and second wire, right? So then here, as you move towards the first wire, the magnetic field increases, right? Magnetic field increases like this. As you move towards the first wire, magnetic field increases, right? And as you move towards second wire, magnetic field increases, but in vertical, here negative y-axis, but along the negative y-axis. Okay, what is the direction of the magnetic field as you move away from the first wire? In negative x direction, this way, right? as you move away from the first wire, the magnetic field increases, but it is along negative y-axis. And as you move away from the first wire, the magnetic field decreases. Okay, magnetic field decreases like this. Okay, and magnetic field increases as you move towards the the first wire. Okay, as you move towards the first wire. Next, magnetic field increases as you move towards the second wire, right? But it is along positive y-axis. Positive y-axis. Okay, so this is the graph. So the correct graph is D. Okay, correct graph is in option D. Yeah. Next question, question number 21. A toroid has 500 turns per meter length. If it carries a current of 2 ampere, the magnetic energy density inside the toroid is. We know that magnetic energy density B equal to mu naught. Sorry, here the magnetic energy density U equal to B square divided by 2 mu naught. Okay, U equal to B square is mu naught. B is mu naught into N into I, that is mu naught square N square into I square divided by 2 mu naught. Here mu naught will get cancelled. So U equal to mu naught is 4 pi into 10 to the power minus 7 into N square is 500 squared. 500 square is 25 into 10 to the power 4. Okay, into I square is 4 divided by 2. Okay, so 2 2s are 4, right? Solve this, you will get 0.628 joule per meter cube. Okay, yeah. Next question, question number 22. In a cyclotron, the charged particle speeds up in d. Wrong. The charged particle takes circular path, but the speed of the charged particle is same in d's. Okay, undergoes acceleration all the time. Correct, it undergoes acceleration all the time, right? Whenever it exists from the d's, okay, exists from the d's, and whenever the charged particle enters into the gap between the d's, it accelerates, right? So it accelerates all the time. Option C, slows down within a d's and speeds up between the d's. Wrong, it does not slows down within a d. Okay, so it maintains the same speed. Okay, and then option D, speeds up between the d's because of the magnetic field. No, this one is also wrong. Okay, so the correct option is B. Next question, question number 23. A number of turns in a coil of galvanometer is tripled, then both voltage sensitivity and current sensitivity remains constant. Wrong, voltage sensitivity remains constant, current sensitivity increases 3 times, or current sensitivity triples, right? Is equal to theta, that is deflection divided by current in the galvanometer, right? I. So now theta by I is NAB by C. C is restoring couple per unit twist, right? So here if N is tripled, right, then current sensitivity is also tripled, right? So current sensitivity increases 3 times, but voltage sensitivity remains same. How? When N increases, okay, when N increases, what happens? The number of length, or the length will also be increases. If length increases, resistance will also be increases, right? So voltage sensitivity is Is divided by R, right? So if Is increases 3 times, then resistance will also be increases 3 times. Okay, so therefore voltage sensitivity remains same, the current sensitivity increases 3 times. Option B, voltage sensitivity increases. Wrong. Option C, both voltage and current sensitivity decreases by 33%. Wrong. Option D, voltage sensitivity remains constant. Correct. And current sensitivity increases 3 times. Correct. So option D is the correct answer. Question number 24. A circular current loop of magnetic moment M is in arbitrary orientation in an external uniform magnetic field B vector. The work done to rotate the loop by 30 degree about an axis perpendicular to the plane. Okay, so this is the circular current loop. Okay, so we need to find the work done to rotate the this loop by 30 degree about an axis perpendicular to its plane, right? Perpendicular to its plane. Here the work done will be 0, right? So why its work done is 0? Here the magnetic moment and magnetic field vector, okay, magnetic moment and magnetic field vector, right? So what is the direction of the magnetic moment and magnetic field vector? The direction of the magnetic moment and magnetic field vector are in 90 degree, right? It is in 90 degree, isn't it? This is the direction of the magnetic moment and magnetic field vector is in this way, right? It's in 90 degree. So the work done will be 0 mb cos theta 1 minus cos theta 2, right? mb cos theta 1 minus cos theta 2, right? So it will be 0 degree only, right? Sorry, it will be 0 only, right? So work done is equal to 0, right? Theta is angle between M and P. It is 90 degree. So cos 90 is 0, right? So option C is correct. Question number 25. The magnetic field at the center O in the given figure is. Okay, so we need to find magnetic field at the center O. This is the given figure, right? So here the magnetic field at the center O due to the circular arc is mu naught I divided by 2r into theta divided by 2 pi, right? So what is the value of theta? Here the value of theta is 300 degree, right? 360 minus 60, 300 degree, isn't it? So B equal to mu naught I divided by 2r into 300 degree minus, sorry, divided by 360 degree, right? So now solve this, you will get magnetic field at the center O as 5 divided by 12 into mu naught I divided by R. Okay, so the correct option is D. Okay, yeah, next question, question number 26. The correct biot-savart's law in vector form. Okay, so the biot-savart's law in vector form is mu naught I divided by 4 pi into dl vector cross r vector divided by r cube. So this is the correct form of the biot-savart's law. Sorry, correct vector form. Okay, so this is the vector form of the biot-savart's law. So the correct option is B. Okay, db vector is equal to mu naught divided by 4 pi into I into dl vector cross r vector divided by r cube. Yeah, question number 27. An electron is moving in a circle of radius r in a uniform magnetic field B. Suddenly the field is reduced to B by 2. Here B dash is equal to B by 2. Okay, initial field is B. The radius of the circular path now becomes. We know that the radius of the circular path taken by the electron when it is moving in a uniform magnetic field which is perpendicular to the velocity of the electron. Okay, so R equal to m into V divided by QB, right? M into V by QB. So from this I can conclude that R is inversely proportional to B, right? R is inversely proportional to magnetic field. Now we need to find the radius of the electron, radius of the circular path taken by the electron when the magnetic field reduced to B by 2. Okay, so R2 divided by R1 is equal to B1 divided by B2. Now R2 divided by R1 is R equal to B1 is B divided by B2. B2 is B by 2, right? So B will get cancelled. 1 by 1 by 2 is 2. So R2 is equal to 2R. When magnetic field reduces to half of the initial magnetic field, then radius becomes double, right? So option B is the correct answer. Next question, question number 28. A charge Q is accelerated through a potential difference V. It is then passed normally through a uniform magnetic field where it moves in a circle of radius r. The potential difference required to move the circle of radius 2r is. Okay, the magnetic field is not changing. Okay, but here we need to find the potential difference required to move the charged particle in a circle of radius 2r, right? Okay, so here when the charged particle accelerates through a potential difference, it gains velocity, right? Here it gains velocity. So kinetic energy of the charged particle is equal to electric potential energy, right? Q into capital B. Okay, Q into potential difference, right? Here half mv square is equal to Q into potential difference V, right? So V is equal to 2qv 2qv, that is potential difference, divided by m, root of 2qv divided by m. This is the velocity of the charged particle, right, when it is accelerated through a potential difference. Okay, now when the charged particle moves in a uniform magnetic field perpendicular to the, here the velocity of the charged particle is perpendicular to the uniform magnetic field, it takes circular path, right? So the radius of the circular path r equal to m into v divided by q into b, right? M into v divided by q into b. Here mass is not changing, magnetic field is not changing, right? Only velocity is changing, isn't it? Velocity is changing, right? Isn't it? Velocity is changing. How velocity is changing? Let's see. Here r is equal to m into root of 2qv divided by m whole divided by q into b, right? So we need to find the potential difference required to move the charged particle in a circle of radius 2r, right? So that is, here when we change the potential difference, velocity of the particle changes, right? Isn't it? Magnetic field is same, charge of the particle is same, right? Mass of the particle is also same, right? So r is equal to here, or I can conclude that from this equation, okay, from this equation I can conclude that r, the radius r, is directly proportional to root of potential difference, right? Now r square is directly proportional to potential difference V, right? Now potential difference V2 divided by potential difference V is equal to here r2 square divided by r1 square. Okay, r2 is equal to 2r, r1 is equal to r. Okay, so we need to find V2. V2 is equal to V into r2 square, that is 4r square divided by r square. Okay, 4r square divided by r square. So r square will get cancelled. V2 equal to 4V. So the correct option is B. Okay, the correct option is B. Next question, question number 29. A cyclotron's oscillator frequency is 10 megahertz and the operating magnetic field is 0.66 Tesla. B, that is magnetic field value, is 0.66 Tesla. If the radius of the Ds, that is D1 and D2, right? The radius of the Ds is 60 centimeter, R equal to 60 into 10 to the power minus 2 meter, then the kinetic energy of the proton being produced by the accelerator is, we need to find kinetic energy of the proton produced by the accelerator, right? That is cyclotron. So kinetic energy produced by the accelerator Ke is equal to q square b square r square divided by 2m. Everybody knows this formula, right? If you don't know how we got this formula, so you can derive it, okay? But in exam it is not important, okay? So how do you derive? You know kinetic energy, right? Kinetic energy is equal to half mv square. You know V equal to qbr by m. Substitute the expression of V to kinetic energy. You will get this expression. Yeah. Now kinetic energy is equal to, what is the charge of the charged particle? Here the charge of the charged particle is 1.6 into 10 to the power minus 19 coulomb, right? That is the charge of the proton, right? So 1.6 into 10 to the power minus 19 coulomb squared, q square, into b square. B square is 0.66 Tesla, right? That is 0.66 squared, right? Into R. R is 10 centimeter, sorry, 60 centimeter, right? R is 60 centimeter. That is 0.6. 60 into 10 to the power minus 2 is 0.6. 0.6 squared divided by 2 into m. What is the mass of the proton? Mass of the proton is 1.67 into 10 to the power minus 27 kg. Okay, now solve this. You will get kinetic energy Ke is approximately equal to 7 mega electron volt. Okay, 7 mega electron volt. So the correct option is C. Solve this. Okay, now you will get the answer in joule. So you have to convert joule to electron volt. Okay, how do you convert joule to electron volt? By dividing 1.6 into 10 to the power minus 19 coulomb, right? Yeah. Okay, so everybody understood how to solve this question, right? Okay, next question, question number 30 and the last one. The magnetic field at the center of a current carrying loop of radius 0.1 meter. Here 0.1 meter is 5.5 times that at a point along its axis. Okay, so at this point, this is center C, right? Here the radius is what is the radius? 0.1 meter, that is 10 centimeter, right? So at C, magnetic field at C is equal to 5 times root 5 magnetic field at point P. Okay, magnetic field at point P, which is lying on the axis of the loop, right? At this point, that is at point P, the magnetic field is BP. Okay, now we need to find the distance of this point from the center of the loop. Okay, so we need to find the distance between C and P, right? Okay, so at the center of the loop, the magnetic field is B equal to mu naught I divided by 2R, right? Mu naught I divided by 2R. Okay, and what is the magnetic field at point P? Magnetic field at point P is mu naught I R square. R is radius of the loop. Okay, divided by 2 into R square plus x square to the power 3 by 2. Okay, R square plus x square to the power 3 by 2. Now here BC equal to 5 times root 5 times BP, right? Isn't it? 5 into root 5 times BP, isn't it? So now I can rewrite this equation as BC is 5 times root 5 BP, which is equal to mu naught I divided by 2R, right? Mu naught I divided by 2R. Okay, so now here 5 into root 5 into BP. BP is mu naught I R square divided by 2 into R square plus x square to the power 3 by 2 equal to mu naught I by 2R, right? Mu naught I divided by 2R, right? Mu naught I by 2, mu naught I by 2 will get cancelled, right? So 5 into root 5 times R cube is equal to R square plus x square to the power 3 by 2. Okay, so now here 5 times root 5 is 5 to the power 3 by 2, right? I can write 5 to the power 3 by 2. 5 to the power 3 by 2. Okay, so now take cube root on both sides. Okay, now this will be 5 root 5. Okay, root 5 into R is equal to R square plus x square to the power 1 by 2, or root of R square plus x square, right? Now take square on both sides. 5 R square is equal to here R square plus x square. Okay, now x square is equal to 4R square. Okay, x equal to 2R. x equal to r. Okay, what is the value of r? R is here. What is the value of r? R is 0.1 meter, right? So x equal to 0.2 meter. R is 0.1, 2 into 0.1 is 0.2 meter. So the correct option is A. Okay. Okay, thank you. Thank you so much. Okay. So if you love this video, please like and share. And if you want to watch more such videos, please subscribe. Okay. Thank you. Thank you so much.